All right, today we are going to decode one of the most important and, most invisible technologies in our lives. I'm talking about cryptography. It's the science of secret writing, and honestly, it's pretty much the only thing standing between your private data and, well, the rest of the world.
I mean, really think about it for a sec. Every single time you log into an account, what happens? You're basically just sending your most sensitive info out into the wild across the open internet. So what's stopping someone from just grabbing it? Well, that invisible shield that protects it, that's cryptography. And today, we're going to see exactly how it all works.
So, here's how we're going to break it all down. First, we'll cover what secret writing even is. Then we'll get into the actual encryption process. After that, we'll look at symmetric versus asymmetric keys. Think of them as the two main toolkits. We'll compare classic ciphers to modern ones, and finally, we'll see where this stuff pops up in your daily life.
Okay, so let's dive right in. First up, what is secret writing? Let's get a handle on the basics of cryptography.
So at its absolute core, cryptography is all about one thing: protection. It's basically a set of rules that lets you take information that's perfectly readable and just scramble it so completely that it becomes total gibberish, complete nonsense, to anyone who isn't supposed to be reading it.
And the name itself, it actually gives us a massive clue. It comes from two Greek words, crypto, which means hidden, and graphy, which means writing. So when you put them together, what do you get? Literally, secret writing. Pretty cool, right?
Now, this secret writing isn't just about hiding things. It actually has four main jobs. First, there's confidentiality. That's the obvious one, making sure your message stays private. Then you've got integrity, which guarantees the message wasn't changed or messed with along the way. Third is authentication, which is just a fancy way of saying it proves you are who you say you are. And finally, non-repudiation. This one's important. It means the person who sent the message can't turn around later and deny they sent it. It's like a full-service security system. The whole shebang.
So that all sounds great in theory, but how does it actually happen? Let's follow a little piece of your data on its journey from your screen all the way to its destination.
Okay, so it all starts with what's called plaintext. That's just your normal readable message. Then it goes through encryption, which is the process of using a special digital key to scramble it all up. And what you get on the other side is ciphertext. Now this is the unreadable, jumbled up data that actually travels across the internet. Once it gets where it's going, the only way to make sense of it is to unlock it or decrypt it back into plaintext. And for that, you guessed it, you need the right key.
And, this process can be surprisingly simple in theory. Let's take a super classic example, the Caesar Cipher. Imagine our plaintext is the word hello, and our key, our secret rule, is just shift every letter forward 3 places in the alphabet. So H becomes K, E becomes H, and so on. The final encrypted ciphertext, KHOOR. Now, of course, this is really easy for a computer to crack today, but that simple idea, that's the fundamental principle behind all the super complex systems we use now.
All right, so that key we keep talking about, it's pretty much the most important piece of this whole puzzle, but it raises a huge question. How do you manage these keys securely? Well, it turns out there are 2 major ways to do it. First up, you've got symmetric cryptography. This is where you use the exact same secret key to both lock and unlock the information. Simple enough. But then you have asymmetric cryptography. This one is a little more clever. It uses a pair of keys. There's a public key that anyone can use to lock the data, but only the matching, totally separate private key can unlock it. Here's a great way to think about it. Symmetric encryption is just like a lockbox. The same key that locks the box is the one that opens it. So if you want to send a secret message to a friend, you both need a copy of that same key. But you see the problem, right? How do you get your friend that key in the first place without someone else getting their hands on it? And this is where the trade-offs really come into play. Symmetric methods, things like AES, which you see everywhere, they are super fast, but they always have that tricky key-sharing problem. On the other hand, asymmetric methods, like RSA, are a bit slower, but they brilliantly solve the key exchange problem. Why? Because you can share your public key with the whole world. It doesn't matter, because only you have the private key to unlock things. So, which one do we use? Well, here's the really clever part. We use both. Your web browser, for example, will start by using the slower, more secure asymmetric method just to safely create and share a brand new one-time use symmetric key. Then, for the rest of your conversation, it switches to that super fast key to encrypt everything else. It is literally the best of both worlds.
I mean, these modern methods are just a world away from where this all began. So to really get a feel for how powerful they are, let's take a quick look at how we got from, shifting letters around in ancient Rome to the crazy complex math we use today.
So those classic ciphers, like the Caesar cipher we just talked about, were all based on simple ideas like swapping letters or shuffling their order. And hey, for their time, they were pretty brilliant. But today, a modern computer could crack one of those in like less than a second. They just don't stand a chance in the digital age. Modern cryptography, on the other hand, it's not about letters at all. It's about math. And not just any math. We're talking about incredibly complex problems, often involving huge prime numbers. It uses massive digital keys and is run by powerful computer algorithms that are crunching billions of calculations every single second.
And what makes modern encryption so ridiculously strong is just the sheer scale of it all. So when you hear about a security standard like AES 256, that 256 refers to a key that has 2 to the power of 256 possible combinations. Now, let me try to put that number in perspective for you. It is a number with 78 digits. It is larger, way larger, than the number of atoms in the entire known universe. So, for all practical purposes, a key that big is, well, it's unbreakable.
Okay, so we've gone through all this theory. But the big question is, where does this stuff actually show up in your life? And the answer, honestly, is everywhere.
Seriously. You see that little padlock icon and HTTPS in your web browser? That's cryptography. You connect your phone to your home Wi-Fi network. That's cryptography. You send a message on WhatsApp that says it's end-to-end encrypted? Yep, that's cryptography too. It is constantly, quietly working in the background of your digital life.
And really, that's the main thing to take away from all this. Cryptography isn't some abstract, nerdy topic just for computer scientists. It is the fundamental technology that makes trust, privacy, and security even possible in our online world. It really is the silent guardian that's protecting your most valuable information every single day. Which kind of leaves us with one last big question. I mean, today's encryption is unbelievably strong, but technology, it never ever stands still. We have things like quantum computers and advanced AI on the horizon, tools with incredible power. So the science of secret writing, it's going to have to evolve all over again. The question is, what new secrets will we need to protect next, and how on earth are we going to do it?